Okay, so let's look at this next problem. A motorcyclist being monitored by radar accelerates at a constant rate from 0 miles per hour to 50 miles per hour in 18 seconds. How far has the motorcycle traveled after 18 seconds? So this is an interesting problem because it really doesn't give me too much information other than the acceleration is at a constant rate at 0 miles per hour to 50 miles per hour, and that happens in 18 seconds. So let me lay some foundation here before we start doing any work. One piece of information is this. The velocity at time t is given by v of t equals s prime of t, where notice s of t, I didn't say s prime, where s of t represents the starting point at time t. So if I knew the starting point at time t and I took its derivative, that would give me the velocity. That's what that's saying. Good? Okay. Let me get another piece of information over here, and that deals with acceleration. The acceleration at time t is given by, so to find the acceleration at time t, it's the same as taking the first derivative of the velocity. If I take the first derivative of the velocity, that would give me the acceleration at time t, which means I would have to take the second derivative of the starting point in order to get that velocity's derivative and then the acceleration. Now, I wrote this part out because it was a very important piece of information and I wanted to make certain you didn't miss it. So I'm hoping you pause the video and write this down. If we are given information about the acceleration of an object, we may be able to integrate to determine the information about the object's velocity and the location. Notice in the story, they gave me the acceleration of this motorcyclist, didn't they? They're asking us how far the motorcyclist has traveled. Well, according to what I've written here, we may be able to determine the location of this motorcyclist by integrating. Now, the location is s of t. Well, this is s double prime of t, and it's all this backward stuff, because if I have to integrate, it's like, well, how do I look at this correctly? So, just put your pen down a second, or your pencil, however you're doing it. Here's how I take a look at this in order to help me out. So my brain can wrap around the fact of what we're trying to integrate in order to find the location or even the velocity of this motorcyclist. Okay? So, again, let me just put your pen down a second. Let me write this down. So what I wrote down was the a of t equaling the first derivative of t, the first derivative of the velocity of t, which equals the second derivative of the position, correct? Of the starting point. Now, what's the opposite of a derivative? Good, the integral. So here's the thing. If I'm trying to find the starting point, if I'm trying to find the s of t, which is that starting point, because when I know the starting point and I know the end point, I know how far he's traveled, don't I? Okay, so to find the starting point, I have the starting point as a second derivative here. So to get rid of two derivatives, you're going to have to take two integrals. One integral will get rid of one derivative. A second integral will get rid of the second derivative, won't it? Okay. Which means here I would have to do the same thing because technically this is an equation, and what I do to one side I do to the other. So that means I would have to take two derivatives, two integrals of the v prime, and then take two integrals of the acceleration. Now just wait. Don't go, wait a minute, what are you doing? I'm trying to figure out how do I find just S of t. They gave me S double prime. I don't care about S double prime. I need just S of t because that's going to give me the location. That's going to give me how far this guy's traveled. So when I take this double integral of a second derivative, it's going to cancel, which tells me to find S of t, this is how I'm going to do it. V prime of t, that prime cancels with one integral. One prime, one integral, canceled. Two primes, two integrals canceled. Which means to find that location, one of the things I can do is take the integral of the velocity. With me? Which means I could also take two integrals of the acceleration, two antiderivatives of the acceleration. Now, this is a process, but what I needed you to see was in order to find that starting point, we've got to take the integral of the velocity. But to take the integral of the velocity, I need to take the integral of the acceleration. With me? Okay. This is going to be our key. This line right here is going to be our key because that's going to help us move forward. That's going to tell us what we need to do. So, and by the way, I could do the same thing on v of t equals the first derivative of the location. If I simply took, and I'm going to write it here, if I simply took the integral of the derivative of s of t, that would cancel. Which means I still have to take the derivative of, or the integral of v of t. So here's another way to look at this. Which is what we have over here. It's the same thing. Okay? All right. So if you need to rewind this part so you can understand it a little bit better. Okay? This is truly key. I understand this. To find the acceleration, I got to take the derivative of the velocity. And to find the velocity, I have to take two derivatives of the starting point. Well, I need to go backwards because I need the starting point. So my brain is like, what do I have to do? Well, this is what I have to do. Integral of the velocity, two integrals of the acceleration. All right? Now, one piece of information that they gave us was that we have an acceleration at a constant rate, which is good. But they told me it went from 0 miles per hour to 50 miles per hour in 18 seconds. They've given me two different time units. That doesn't work very well. If our rate is in mile, or our acceleration rate is in miles per hour, then the time in which it occurred needs to be in hours. So, first things first, one of the very first things I need to do right now is I need to convert 18 seconds into hours. Why? Because they gave me a speed of 50 miles per hour. So, some of you may not be very good at converting, and some of you may be excellent at converting, and some of you may be somewhere in between. I'm going to show you a conversion technique that I learned when I was in a high school chemistry class. Never forgot it because it was super easy. I didn't really care about numbers. I cared about the location of the units. So I'm basically going to set this up like a multiplication problem of fractions. So I have 18 seconds over 1. Now I need seconds to go away. I do know that 1 minute is equivalent to 60 seconds, don't I? So I'm going to put 60 seconds at the bottom and 1 minute on top. And some of you may be going, why? I have seconds on top on the first fraction seconds on bottom on the second fraction, I can cancel those units out. With me? Yeah, all we're doing is multiplying fractions. Remember, I'm trying to convert to hours. Right now, my seconds canceled and I'm left in minutes. Well, I don't want minutes, I want hours. So, 1 hour is 60 minutes. So, where are you going to put those 60 minutes? Yes, at the bottom of fraction number 3, so you can cancel the minutes that's on the top of fraction 2, and 1 hour at the top, which leaves you 18 over 3,600 hours, which when you get your calculator out and you do the division, you end up with 0.005 hours. So that's not a whole lot of hours, is it? That's 5,000ths of an hour that it took this guy to go from 0 to 50 miles per hour. Good? Okay. So, pause the video if you need to. Write some of this information down. Rewind it. Make sure you take good notes about this. All right? Make sure you keep this piece of information handy as well. And we're going to continue this problem as soon as I erase the board. Okay, so hopefully you got that information written down. And I know it's new, so it's kind of like, wait, I'm trying to wrap my brain around it. I kind of got it, kind of don't. Understood. I did write 2 pieces of information down. When we went backwards, what we found out was to find that starting point, we had to take the integral of the velocity. And to find the velocity, I have to take the integral of the acceleration. So these are 2 key pieces of information we're going to need. So I wrote them down so we could remember them. Good? Okay. Now, let me go back to the problem. The one thing they told us in the problem is that that this motorcyclist accelerates at a constant speed. So I know that acceleration is constant. And that reminds me of a linear equation. One of the things that we don't have is an equation. So right now, we actually need an equation. So I'm going to write that down. Need an equation. And the fact that this tells me it's constant tells me I'm dealing with a linear equation. Okay? Which means you need a slope, right? The slope is what's really going to help us out. So you're like, well, how do I need a couple of points. I get it. I'm dealing with 2 pieces of information here. I'm dealing with time and I'm dealing with speed, correct? The question is, which is dependent on the other? Is time dependent on how fast you go, speed, or does the speed depend on how much time has passed? Yeah, speed depends on how much time has passed, right? After 0 seconds, you're not at like 50 miles an hour. It's taken time to get to 50 miles an hour, hasn't it? So your time is your independent or your X. Your speed is your Y or your dependent. Now, I need 2 points to help me out here. One point is very simple. For acceleration, at 0 time, he had 0 speed. Agreed? The other piece of information that we had was that after 18 seconds, this guy got up to 50 miles per hour. Well, remember, we converted the 18 seconds into hours, didn't we? And that was 0.005 hours, and that's when he got up to 50 miles per hour. Agreed? Okay. By the way, let me kind of do this for our units. This is in hours. This is in miles per hour. Okay? Okay. So, to find our acceleration, which is really what this slope is doing, it's actually finding the acceleration. To find the acceleration, I'm basically going to be using a slope formula because it's constant. So, the difference of the y's over the difference of the x's. So I have 50 minus 0 over 0.005 minus 0, which gives me 50 over 0.005, which gives me 10,000. Agreed? Did you get the same thing? Okay. Now, most people don't know what units that 10,000 is in. You're like, well, if that's acceleration, what's the units? Is it still miles per hour? Actually, it's not. So here's how I'm going to show you what the units are. Units for acceleration. In the formula we just did, we had the 50 minus 0 on the top, which represented speed, which was in miles per hour. So I've got miles per hour over, now the 0.005 minus 0 represented the time, and the time was in hours. So divided by hours. Now, I'm going to write this with our old-fashioned division symbol. I have miles per hour divided by hours, right? And when you divide fractions, you multiply by the reciprocal. So miles per hour multiplied by 1 over hour will give me miles per hour squared. That's the unit of acceleration, is in this case miles per hour squared. Acceleration is quick. It's time over time, okay? So your acceleration equation in this case is 10,000 miles per hour squared. That's my acceleration equation because the acceleration was constant. And in this case, it's 10,000 miles per hour squared. Good? Okay. Remember, we need to know the distance this motorcyclist has traveled, right? All I know right now is the acceleration, which is good. I've got at least something to work with. I didn't even have that before. According to what we wrote down here, if I take the integral of acceleration, that will at least get me the velocity, won't it? Okay, I know I don't want to stop at velocity, but at least if I take the integral of acceleration, it gives me the velocity, right? And if I look ahead, once I find the velocity and take the integral of that, then I can find my starting point, can't I? Okay, so first things first. Since we have acceleration, let's take the integral of the acceleration to find velocity. At least I can find the velocity. Okay? Okay. So, next, we can find the v of t. We can find the velocity. And to find the velocity, it is going to be the integral of 10,000 dt. Cool? Okay, and when I take that integral, I get 10,000 t, right? Plus a constant. You're like, why a constant? You didn't give me the time to go over with me. You didn't give me from here to here. You didn't give me a definite integral. You're like, oh man. Okay, but don't freak out on me, all right? Because we do know a piece of information that's going to help us get that constant. What we do know is something they told us in the very beginning. They said the velocity at time 0 was 0. Okay, well, that's going to help because they gave that to us in the problem. Since the velocity at time 0 is 0, to find c, we simply get to plug in that 0 for the v of t and for the time itself, and that tells me my constant is 0. So yay! Hopefully that was not too big of a shock, which means my velocity formula in this case is just simply 10,000 t. Now, here's the interesting part. You're like, well, what's the units on that? Acceleration was miles per hour per hour. When I integrated it, it became velocity, which by the way is also known as speed. And when I did that, it got rid of one of these hours. So the velocity units is just miles per hour. Cool? Okay. Now I've got the velocity. If I integrate the velocity, it will help me find the distance, won't it? Okay, so I'm hoping I've got enough board space, so bear with me. We are going to find s of t, we are going to take the integral of the velocity, which was 10,000 t, and take it with respect to t. So that's why it's dt there. Good? All right. Take the antiderivative of this. You get 10,000 times 1/2 t squared plus that c again, that constant again. Correct? All right. So 10,000 times 1/2. What's that going to give you? Yeah, that's going to give you 5,000. Good. 5,000 t squared plus c. Agreed? Agreed. Now, I've got myself a little bit more board space. We're doing good here. So we can finish off this problem. So I'm going to bring this up. So far we have that the starting point of t is going to be 5,000 t squared plus c. Now, like, there's that c again, I know, but it's not so bad because now let's think about this. At time 0, so the starting point at time 0, wouldn't that just be 0? We haven't gone anywhere. The distance would just be 0, wouldn't it? So if we plug it in, 0 equals 5,000 times 0 squared plus c, which means c equals 0 again. Woohoo! This piece of information, s of 0 equals 0, was to find c. Which means your distance equation, right, the starting point equation, s of t, is going to be 5,000 times t squared. Yay! Constants are dropping out. Okay, now I got a question for you. Acceleration was in miles per hour per hour. We took the antiderivative and got the velocity. The velocity is in miles per hour. I integrated that. What do you think my starting point is going to be in? Yeah, the starting point is simply going to be in miles. So I can find how many miles this motorcyclist traveled if I knew t. Agreed? So my question to you is this. Do I know the time? Yeah, I do. 18 seconds. But remember, we're in hours, right? We're in hours, and we converted those 18 seconds into hours. So, what do we know? We know that the time the motorcyclist traveled was 18 seconds, but that translated to 0.005 hours. So to find that distance that this motorcyclist traveled, we need to plug in the 0.005 for the t. So now we have to square the 0.005 and then multiply by 5,000. You get your calculators out and do that work. I got my little cheat sheet out so I can get that work, or get my answer. And I ended up with 0.125 miles. Did you get the same? Yay! Hold on though. The directions say please put it into a fraction or an integer. So this is equivalent to 1/8 of a mile. That's how far this motorcyclist traveled. In those 18 seconds, he traveled 1/8 of a mile. Cool? Okay, recommendation, watch this problem again because the next problem is going to be based upon you knowing how to do this one. Okay, last problem. Did you read it? Let's look at it again. We have a cyclist. So a bicyclist accelerates at a constant rate from a standstill to 15 kilometers per hour in 90 seconds. Wow, that sounds familiar, right? We have this acceleration being constant again, don't we? And they asked me two questions. One question is how fast the cyclist is going. The other question is how far the cyclist is going. So that kind of sounds like the last problem, right? So a couple things to remember. To get the velocity, which is how fast the cyclist is going, I need to take the antiderivative of acceleration. To get how far the cyclist is going, I need to take the antiderivative of the velocity. Cool? Okay. So let's get to part A first. Let's just deal with part A. Part A says how fast is that cyclist traveling after 25 seconds? Well, a couple of things. First and foremost, they told us the acceleration is constant, right? That's a good thing. The next thing is we know that based upon what we've done before, acceleration being constant means it's a linear problem that we have going on, which means we're kind of finding a slope. And that slope is going to be comprised of 2 points, time being your independent or your x, and speed being your y or your dependent, correct? Okay. Now, before we even do any of that, they told us that the bicyclist accelerates at a constant rate from from a standstill to 15 kilometers per hour in 90 seconds. Well, isn't that nice of them? What are we going to have to do? Yes. So first, convert 90 seconds into hours. Let's at least get the units right. Which means, again, my wonderful high school chem days, this is how I learned to convert, because it's not really based upon the numbers, where I put the numbers. It's based upon where I put the units. And when I set it up as fractions, it's very easy to see where I put the units. So I have 90 seconds over 1 times 1 minute over 60 seconds. So I cancel the seconds from the bottom and the top, times 1 hour over 60 minutes. So I cancel the minutes from the bottom and the top, which gives me 90 over 3600, which is 0.025 hours. If I look at my handy dandy cheat sheet, that answer is yes. Cool? Okay. Now I can get back to that acceleration. 2 points. At 0 time, the speed is 0. At 0.025 hours, the speed is 15 kilometers per hour, right? Okay, and so by the way, let me make that notation. This is in hours, time is, speed is in kilometers per hour. Okay, so as I find the acceleration with respect to time, looks like I'm doing 15 minus 0 over 0.025 minus 0, which is 15 over 0.025, which my handy dandy cheat sheet tells me 600. Did you get that? Yeah. And so now I need to know my units. So the units for acceleration. Remember, the numerator was speed, which is in kilometers per hour. The denominator was time, which is in hours. So, looking a little familiar, yes? If I take kilometers per hour and divide by hours, I am going to do kilometers per hour and multiply by the 1 over the hour, which is going to give me kilometers per hour squared. So my acceleration is 600 kilometers per hour squared. Cool? Okay. Now that I actually have acceleration, if I integrate it, I can find velocity, which means I can find how fast this guy is going, which is what they're asking me in part A. I haven't even found how fast he's going yet because I needed an equation to get started. So maybe you need to make that note for yourself too. We need an equation. And this is how we were getting the equation. So, to find the velocity, which is how fast the guy is going, we are going to take the antiderivative of the acceleration, which is just 600. And we're taking it with respect to t. I'm not going to insult your intelligence at this point. You get 600t plus c is the antiderivative. I need to find out what that constant c is. Well, think about it. At time being 0, the velocity, or how fast the guy is going at time is 0, isn't it? Which implies your constant is going to be a 0, correct? Yeah. So that means my velocity equation is, or function is 600t. Now what do you think the units is? Remember, acceleration was in kilometers per hour squared. Yeah, so the speed is going to be in kilometers per hour. So we have the velocity formula as 600t. And now we need to plug in for t, don't we? Okay, so hold on. Part A says how fast is the bicyclist traveling after 25 seconds. All right, that's 25 seconds. I don't need seconds, I need hours. So we have another conversion to do, don't we? Okay, so 25 seconds over 1 times 1 minute over 60 seconds times 1 hour over 60 minutes. I'm canceling my minutes, I'm canceling my seconds. This is going to give me 25 over 3,600 hours. Right? Okay. Now when I punched that into the calculator, that was not an exact number. That was going to give me a funky little decimal, which means I am going to leave it as a fraction. I'm leaving it as a fraction so I can have as accurate an answer as possible. So I'm taking the velocity at 25 over 3,600 hours. And that's going to be equal to 600 times 25 over 3,600 hours, which is going to give me 4.17 kilometers per hour. Good? Okay. Be careful, because it would have been very easy to have plugged in the 0.025, but that was 90 seconds. Part A wanted 25 seconds. Now I got to get to part B, but I need board space. So I'll be right back after I get some board space. Here's part B. Remember, it's still here. The location, how far they went, we find it by taking the integral of the velocity. Well, in part A, we found the velocity. So I wrote it up here again. The velocity with respect to time is 600 t. Its units were in kilometers per hour. In part B, they want to know how far the cyclist has traveled after 90 seconds. Gratefully, we already figured out the 90 seconds was 0.025 hours. What we need is the formula for that distance. And to get it, we have to take the antiderivative of the velocity. So to get that distance, we're going to take the antiderivative of 600t with respect to t. I'm not going to insult your intelligence. You know how to do this. We have 600 times 1/2 t squared plus that constant. So the distance formula with respect to time is 300 t squared plus that constant. Okay, need to find the constant, right? So, to find the constant, what do we know? At time t, the distance is 0. So, s of 0 is going to give me 0, which means c, therefore, remember those 3 little dots in a triangle mean therefore c is 0. Plug it in, you'll see that c is equal to 0. Which means we have the formula for the distance. S of t is equal to 300 t squared. Good? Yay, we have the distance formula, how far somebody's traveled, so to speak. And now I need to know how far this bicyclist has traveled in 90 seconds. So, yep, in 90 seconds, which is the same as 0.025 hours, the distance in 0.025 hours is going to be found by doing 300 times 0.025 squared. By the way, before we get that answer, what's my units? Yeah, just kilometers. Acceleration in this case was kilometers per hour squared. Velocity is kilometers per hour. The distance is just kilometers. Every time you back up, we're losing that time. So I ended up with 0.1875 kilometers. Good? Okay. These last 2 problems were really brain teasers, so to speak. Make sure you go over them again. Write down whatever notes you need to. Because once you catch the fact that you have to take these antiderivatives to work backwards, then you're kind of home free, so to speak. Got it? Okay. You have fun with this stuff. I'll catch you on the flip side.